Okay, I want to start out talking about the third perspective that we've learned about. Remember that perspective number one is kinematics, perspective number two was forces, perspective number three is work and energy, and then the fourth and final perspective on our universe is going to be impulse and momentum. So we're skipping over forces for now. But you should remember all of the basic underlying principles associated with the force perspective. You've been using it an awful lot. And as it relates to rotation, you should remember this from last year as well. So I'm going to switch up the order a little bit because it's going to be a little more useful for us in this way. Now I want to compare some of the foundational equations that we use for conservation of energy and work and energy principles between translation and rotation. Okay, so you can see the direct comparison. Our first equation here is just the definition of work, and we learned that work was equal to F dot D, which is the same thing as F times D times the cosine of phi. In rotation, work is defined as the rotational equivalent of force, and then the rotational equivalent of displacement, which is delta theta. We can ignore the cosine phi aspect of that for rotation because that's implicit to the torque, the way the interaction occurs. So it's still of the same basic form, force times displacement, force times displacement. Kinetic energy is equal to 1/2 mv squared for translation, and in rotation it's still 1/2 times rotational mass times rotational velocity squared. So it's still of the same form. Now you'll notice that when it comes to the laws and the theorems, virtually nothing has changed. W net equals delta K, W net equals delta K. That's the work energy theorem. Delta E is equal to 0. That is conservation of mechanical energy. And delta E is equal to WNC, or the work done by non-conservative forces. This is a more universal form of conservation because it will include work which is done by friction or possibly work which is done by a thrust force. But the big idea between these, the differences you must recall, is that for delta E to be equal to 0, the system must be isolated. And when delta E is equal to WNC, it is not isolated. And if you don't remember what exactly that means, whenever it's isolated, we could say that F net is equal to 0. And whenever it's not isolated, then F net is no longer equal to 0. In other words, the center of mass of the system, that's the important part, the center of mass of the system is going to accelerate if the system is not isolated. So for example, if you're driving a car up a hill and the car is speeding up as you drive up the hill, clearly something is adding energy to that system, because if the car were just coasting, it would definitely be slowing down. So that's the primary difference between the two. But this is why, when you look at W net equals delta K and these laws and the theorems, I always write them in the simplest form possible, and I teach it to you in the simplest form possible so that you can clearly see as you go from one phenomena to another that the laws and the theorems do not change. What changes are the definitions, and we see that between work and kinetic energy as we go from one to the other. It's of the same form, It's just now we have to put it in terms of the variables of the phenomena. So for rotation, we no longer have force, it's rotational force. It's no longer displacement as we understand it in kinematics for translation, it's now displacement for rotation. Okay, so that's our basic review of the foundational energy work and energy principles for rotation. I'm not going to go into great detail about energy and work and the principles behind conservation because we've already learned that before. So all I'm going to be doing here in the rest of this clip is just a little bit of embellishment for clarity as it pertains to rotation. The first thing that I want to discuss here is that when we're talking about conservation, E was defined the mechanical energy. Remember, E is mechanical energy. When we did translation, we defined that as K for translational motion plus UG, gravitational potential energy. And when we included springs, we had UE for elastic potential energy. All right, well, E now for mechanical energy is also going to include K rotational. And that's it. I mean, that's really the only difference between conservation with translation only and conservation that includes rotation. All right. And so, when it comes to including K rotational, you just have to ask yourself one basic question, and that is the object rotating? Because if the object is rotating, then there's, well, rotational kinetic energy. Okay. So that's that. Okay, so this is probably the biggest and most important principle that I can give to you as it relates to doing conservation of energy with rotation. And that is, if the axis of rotation is in motion, and here's the other proviso, at the instant of your analysis, then you must include translational kinetic energy. This goes back to what we did with deriving the parallel axis theorem. And I'm going to do a separate video where I go through some examples of this so that it will be clear to you. It's not appropriate in this video, so I'm not going to do it in this one. But I am going to do a video where I go through a couple of examples of this to make it perfectly clear, or at least hopefully perfectly clear. So if the axis of rotation is in motion at the instant of your analysis, if you just take a picture and you say, what's moving in this picture? Then you must include translational kinetic energy. If the axis of rotation is stationary at that instant, then there is no translational kinetic energy.